Okay, we'll get started today. Couple quick announcements. The midterm is this Friday. I've posted the midterm study guide. I strongly encourage you to look at the midterm study guide because it is the midterm. And I say this every year, and I don't think people believe me, but that's the midterm. In the same order, every part, every bullet is the midterm. So you don't need to study anything that isn't on that study guide. That's helpful because we cover a ton of stuff in this class, and I recognize that. This allows you to greatly reduce the quantity that you have to study for the exams, right? A couple other things is the midterm review. We're going to hold a review tomorrow in this room from 5 to 7. If you can't make it, I record those and I'll put it on YouTube as quick as I get home. There's normally homework hours from 5 to 7. Ashley has very graciously been voluntold that she'll do her TA hours for homework from 7 to 9. So everyone, I'd say thank you to Ashley and bring her a Snickers bar or something so she's not hangry. And then we're going to have an extra TA midterm review. If you can't make it to mine, if you just want to come and ask more questions, the TAs have seen the midterm, so they're going to be helpful as well. They're going to hold a separate study review on Wednesday from 5 to 7. All of those will take place in this room. In the past, it's never been the case that this room was busy. If it is busy, if it's booked for something, we will leave a note on the door and we will make a Canvas announcement and we will move to probably the room next door or wherever we can find. Okay? So that is midterm for this week. Okay, let's talk about our learning objectives for today. We went a little bit slow yesterday. I'm going to try and finish most of the chapter today, which means we need to figure out a few more key reactions, right? We need to talk about the lever rule. That's going to allow us to talk about the amount of each phase. And then we're going to talk about non-equilibrium cooling a little more, the lamellar structure a little more, and if we have time, we'll get to the steel phase diagram. Okay? So let's dive into it. Where we left off last time, we explained what a eutectic was and a paratectic reaction was. And there's a million others, right? So I'll show you how many there are. We're not going to study them all in this class, but if I find it. Okay. Here's a diagram that shows like every type of kooky reaction that you can have. Like they're all there, right? You've got monotectoid. What would monotectoid be? A monotectoid is this single phase reacting to form. This is going to be a two-phase mixture because this is a congruent melting, not line compound, but single phase, right? So one phase going to two different ones when you have a critical immiscibility gap. So it's a special type of eutectoid. It's a eutectoid where there's a solid immiscibility gap, right? So it doesn't matter. We're not going to learn all these. The ones that I want you to know in this class are, let me just circle them. Paratectic, let me do a different color. We want paratectic, eutectic, monotectic. It doesn't like when I draw on figures in ENDNOTE, which is weird, right? It's the ones up here that aren't in the end of the chapter etc. notes. They'll be in the main section, like monotectic, right? Or like up here we had paratectic. Those are the ones that matter. Okay? Okay, let's do a couple more definitions. There's something, we talked about line compounds last time. Now let's talk about congruent melting versus incongruent melting. A congruent melting compound is one that goes from solid to liquid with no change in composition. Right? Solid to liquid, or liquid to solid if it's a solidification, right? But there's no change in composition. So if you're at, in this diagram, say right here, you're at 33 atomic percent calcium, and you heat it up, you're going to turn into, just above this point, you're going to turn into 33 atomic percent liquid, right? So it goes completely from solid to liquid, and there's no change in composition. Now contrast that with this point. If you're heating up this compound right there, this is also a line compound, but as soon as you're above this point, you have, first off, a two-phase mixture. You don't have a pure liquid, because it's a two-phase region, right? And your liquid has this composition, which is maybe 15%. So it changed composition. So incongruent versus congruent melting, that's the difference. Is there's a change in composition or not? Yeah, Julia?
If you have a two-phase, if we want to find the percent composition of each component, we go to the left
Great question, yeah. The one that borders the phase you're interested in will give you the composition of that phase. So since liquid is on the left over here, just above this line, this would be your composition of liquid. And your solid, you go to the right, it's a line compound. It has that 33 atomic percent. What if we were over here? What if I said you start out at 50, you go just above this eutectic reaction. What's the composition of liquid that forms? You say, easy. It's the eutectic composition, which is, maybe like 62 or 5 or something. Whereas the solid in this case is now going to be the same. It's at 33 atomic percent calcium. Any questions on this? Congruent versus incongruent melting? Technically, your pure calcium is a congruent melting compound too, right? Pure calcium, when it does melt up there, goes to pure calcium liquid with no change. So technically those are congruent melting, but we usually don't talk about them like congruent melting. We're typically talking about intermediate phases as congruent or incongruent melters. Okay, how about this? In this diagram, it was really nice because they labeled what the chemical formula were of these intermediate line compounds. This one's labeled Al4 calcium, right? This one's aluminum 2 calcium. The question is, where on earth did those numbers come from, right? So you're given the value here in atomic fraction. That means that you could literally take all the atoms, and this is saying that 33% of your atoms right here are calcium. So it should make sense that out of a 3-atom formula, one of your 3 is calcium and 2 are aluminum. Does that make sense? Let's do it over here. This is at 20 atomic percent calcium. So 20%, that means out of 5 atoms total, right? If that's your total, then one of them would be calcium. So 4 aluminums, 1 calcium. 1/5 of them is calcium. So it's easy if they land on one of these numbers like 20, 33, 50, 75. Those are easy fractions. What if it's a weird one, right? What if the line compound is like right here? Let's see. At 16%. What do? What's that formula? Right? If it's 16%, maybe that's not as obvious to people what fraction that corresponds to. So what should you do? Maybe turn to a neighbor and discuss what might you do to figure out the formula there. Okay, anybody have a thought? Maybe you remember what 16 corresponds to, but I wouldn't. So what do? Any thoughts? Yeah, Ashton. So good question. Before we go down that road, do we need atomic percent or do we need weight percent? So to figure out the chemical formula, it's all about atomic ratio. So you don't want to convert to weight percent. I'm going to give you the opposite example in a moment. I'm going to give you weight percent. We're going to switch it to mole percent or atomic percent, and then we're going to figure out the formula. But here we're already given atomic percent, so you don't want to convert it to weight percent. But you start out with 16 atomic percent calcium. What do you think?
Just do Al84 and then Ca16 and simplify it.
Yeah. That's really what we're doing. We're saying, okay, that means that there's 84 parts, what? What is this given? Oh, Al, right? 84 parts Al, 16 parts calcium. You could just start dividing this thing and simplifying it. That would be one approach. What I suggest you do is you take the 84. By the way, 84 came from 100 minus 16, right? I take that 84 and I divide it by 16, and you're going to get the answer is about 5. It's going to be close to a whole number of 5. What that means is that for every 5 parts of aluminum, there's 1 part calcium, right? You got your formula. It's going to be aluminum, 5, calcium. Or in other words, 16% is 1/6 is the fraction that you might not have remembered. Any questions on this? Just dividing these things and looking for a very close to whole number. Yeah?
So it doesn't have to be an exact number?
No, because we're going to do an example where it's tricky, okay?
So where do the extra atoms go?
It means that you didn't estimate it just right, or that it's a non-stoichiometric compound, right? Because some of these things are really easy to read. Like, how did I know that was exactly 33% though? I know it because the chemical formula is written. If I was just reading this off there, I'd say, okay, 20, 30. What if I said 34, right? Well, let's just do it. What if I assumed that was 34 because I wasn't thinking straight? That means that the other one has 66, right? So I'm going to take 66 and divide it by 34. And I come out with 1.94 rather than 2. So that's telling you, oh, I just didn't read it right? The formula is probably 1 to 2, right? Not 1 to 1.94. If it's 1.94, and those technically exist, but they're atypical, they typically exist as whole numbers here, right? Most of the time. Any questions so far? Yeah, Julia?
I just, never mind. I answered mine.
It makes sense? It clicked right then? Okay. All right, how about this one? What if your phase diagram is in weight percent and not atomic percent, which is very common. Most diagrams, I'd say, are actually in weight percent, not atomic percent. So we're going to do this one as a clicker example. And the compound you find is located at 81 weight percent, 19 weight percent, right? So let me pull this up. Okay, what I'm asking you is to figure out what would be the chemical formula, and it's a simple one. These are whole number ratios of the compound that you find located, let's say it's a line compound, located at 81 weight percent lead, 19 weight percent magnesium. You will need the molecular weights because we just said this. The trick, if you're given weight percent, you need to turn it into atomic percent so you can take the ratios. So go ahead, convert that to atomic percent, figure out the ratio. And you can enter this one in as numbers. So let's say you think the answer is like lead 5, magnesium 3. That is not the answer. If you thought that was it though, you could type it in just like that with no spaces. You could do magnesium first, you could do lead first. It'll all work. Thank you for doing those reading quiz questions. It's really, really helpful. If it's a lot for you to handle, like lean on the other TAs too, and they can help out. Okay. I really appreciate that though. I have homework 3 solutions I sent around. I totally thought that those were done, but they were like not even close. So now they are. Anybody need help? The number goes after. When you put your answer in, the number always goes after the element, right? Like I've written it here, PB5, Mg3, if that's what you think it is. Top hat's not working? Oh! Okay, now it should work. Now you should be able to put answers in. What's up? You can leave it or you can have it or not have it, and it'll give you the right answer. Traditionally, you don't write the 1. Yeah, I've programmed it so it'll accept all. I think I've got all the combinations of answers that people might put in.
How many students are in this class?
I used to know it. Was it 150?
Yeah, that's what I thought too.
I think it's around 150 this semester. I programmed it to accept many different varieties. That would work. That's not the right answer, though. Yeah. Okay, we're just going to do 2 more minutes on this. Okay, we're going to wrap it up. Get your final answers in. Okay, final answers in. We're closing the poll. Okay, we're closing it. Okay. Say, what do people think? We're going to see all sorts of things here, right? Oh, so capitalization. You guys, all right. I will go back through and program it to accept non-capitalized. But in general, when you write chemical formula, you got to write capital M, right? So I'll correct it so it'll accept that. But the answer, if I'm not mistaken, is, well, let's do it together to find out. All right? So we need to figure out how many moles of lead we have. So if it's 81 weight percent, then assume that you have 100 grams. That means 81 of your grams is lead, right? So 81 grams of lead. Whoa. OneNote doing OneNote things. All right, let's try that again. 81 grams of lead. We're going to multiply that by the molecular weight of lead. 207.2 grams. Oh, we're going to divide it by, excuse me. In 1 mole of lead divided by 207.2 grams, right? And then the same thing over here, we're going to assume 19 grams of magnesium. We're going to divide it by its molecular weight. In 1 mole of Mg, we have 24.3 grams. So what is 81 divided by 207.2? One more time, Elias. 0.739? Oh, 0.39. All right, what about magnesium? 0.78. So just looking at it, you can tell that there's twice as much magnesium as there is lead, right? For every 1 mole of magnesium, you've got 2 moles. For every 1 mole of lead, you've got 2 moles of magnesium. So the formula is going to be PbMg2. Any questions? You could divide it and see that it's about 2. If you put a 1 there or not, it'll give you the correct answer on top hat. But the convention is to leave off 1. You don't have to write 1. But it'll give you the right answer either way. And then the only thing I need to do is program it to accept uppercase and lowercase, so I'll go back and make those acceptable values. But in general, do it uppercase, right? Each element starts with an uppercase letter. Any questions on this? Yeah, Anthony? Yeah. So we know that we've got 0.39 moles of lead, and we've got 0.78 moles of magnesium. If you take 0.78, if we take 0.78 and we divide it by 0.39, I get 2 exactly, right? So that tells you that there are 2 moles of magnesium for every 1 mole of lead, or 2 atoms of magnesium for every 1 atom of lead, since mole ratio and atomic ratio is the same thing. Okay? Everybody could do that on a test. If I gave you a weight percent, quick convert it over, no big deal. Okay. There's other examples. I think this YouTube example is a little bit trickier because phase diagrams don't have to be between individual atoms, right? So let's show you an example of what I'm talking about. Some diagrams are more complicated in that they show the end members are different compounds themselves. Like this one's in the book. On the left-hand side, you've got MgO, and on the right-hand side, you've got Al2O3, right? So you would do this the exact same way, but instead of solving for number of moles of aluminum, it's now aluminum oxide. Over here, it's moles of magnesium oxide. But if you figure out that there's like a 2-to-3 ratio, then you just add 2 of these formulas and 3 of these, right? So for example, this is a really good one right here. MgAl2O4. If you look at that, this is in weight percent, right? If you were to convert that to atomic percent, since we know what the formula is, we know where this line would be at in the middle of it. It's going to be at 66% what? Sorry, this is 1-to-1. This would be located at 1 part MgO and 1 part Al2O3. And if you add those formula up, you get 1 Mg, 2 Al2, and 3 plus 1 is 4 oxygen. Does this make sense? So it's the exact same approach if it's elements or if it's compounds. Can I answer any questions? There's one in the book like this on the homework, I think, that you have to do. Okay? By the way, is this a line compound? This what's called a spinel. It's an incredibly important crystal structure. My entire PhD was this structure, right? We'll learn about why in a few chapters when we talk about crystal structures. But it's not a line compound. Look at this. It can have one, formula that spans a really large gap of composition. Now, does that mean that this is the correct formula for that whole range? No. This is the correct formula only for exactly one part of each. But what this means is that you can have extra magnesium or extra aluminum. You can change the oxygen ratio too as well in these things, okay? And that's what the homework question has you do from this week, okay? Let's keep moving. Or any questions I can answer before we move on? Okay. Yeah.
Question's kind of a follow-up of something you said last time before the class ended.
Yep.
You talked about how line compounds are always vertical lines, but vertical lines aren't always line compounds.
Correct.
Okay, totally different.
Good question. A line compound has to be a vertical line, but not every vertical line is a compound. The way that we know that these are line compounds, if these weren't labeled, right, which they won't be on the exam, is you have to do your 1-2-1-2 rule. If at any point, like make an assumption, like pencil in lightly, say this is a vertical line, it's probably a line compound. Pencil it down as you think it's a line compound, start doing your rule, and if it's messed up anywhere, then it's not a line compound. That is the surest way I can think of to figure it out. Okay? So make an assumption and then test it. Okay, keep moving. Let's keep going. All right. So we already talked briefly about cooling under equilibrium conditions versus non-equilibrium. I'm just going to remind you a little bit what we were saying. Let's say you're cooling down right here. And again, this is a phase diagram that has complete... That is so strange. Why can I not draw on those? Or will it stay this time? All right. This is an example of complete solid solution between, look at this is Mg2SO4. That's that same crystal structure we were talking about, but instead of aluminum, now it's silicon, right? And the ratio is slightly off, but this is also, it's gone. So OneNote's being super awesome today. Mg2SiO4 to Fe2SiO4, right? So complete solid solution all the way across there. That must mean that they're the same crystal structure if they go all the way across like that. Now imagine what happens is you start to cool this thing down. The second that you touch this point in temperature, as you cool it down to that point, oh geez. I might just restart this. I might restart it. Let's do it, because I don't want to fight with this. At that point, this temperature is, maybe 1750 or something. The very first solid that forms, oh geez. The very first solid that forms will have this composition, something like 18%. And if you cool it down really slowly, then the composition of that solid is going to keep on changing until you get to this point, and then your solid will be at that composition. And what we're assuming under thermodynamic phase diagram, where it reaches equilibrium, is that it's happening slowly enough that your atoms that were initially rich in magnesium silicate are able to diffuse and add iron silicate into the center of that glob, right? Because if we were to draw these things, right, it starts out as little crystals and it gets larger and larger. And we're assuming that it's going to reach equilibrium, and that's not always the case. So we mentioned this at the beginning of this chapter, that coring can occur, where basically it might be really rich in the center, and then these things grow outward, and they have a gradient in your concentration because you're cooling it down fast enough that you're not allowing these two things to mix together. Okay? That's non-equilibrium cooling or coring. Okay? Now, as these things grow together, right, as these things grow, when it's completely solid, you're going to achieve big regions that don't have the same orientation. What does orientation mean? So take a look at the students in this middle section. The rows are located kind of like, but on the sides they're tilted a little bit, right? This is like straight like that, and this one's off at a different angle. Your atoms can do the exact same thing. They can be tilted a little bit. And so if we were able to zoom in on these different regions, maybe this one's oriented like that in a nice square grid. But this one next to it doesn't have to be the exact same. It can be off a little bit. That make sense? We call the junction between those two grains a grain boundary. And they are enormously important. We're going to talk about them so much more this semester, right? So these little islands that started out, when they grow together, they form grain boundaries, right? And the regions in between the grain boundaries are then the grains, right? Now, how do we do the lever rule? The lever rule lets us know the amount of any phase of our phase diagram at any temperature, right? So if this lets me draw on it, which I'm skeptical of. If our initial composition was 40, then at this temperature, right there, we know that we've got a mixture of alpha plus liquid. Weird crap going on there. How do we know how much alpha and how much liquid? We do the lever rule, okay? The lever rule is as follows. We're going to take this distance. We're going to take this distance. Things are just disappearing. And we're going to take the total distance. This is just like comical. Like somebody's doing this somewhere? Like somebody has like a mouse? Okay. From those three distances, we can figure out the fraction of the different phases present. Here's how it works. Super helpful. I might have to re-record this later. But if you want to figure out how much liquid there is, then the closer to that line, the liquid line you are, the more liquid you should have. So here's what you do. You take the gray section, the one on the left, divide it by the red one. So you take the one opposite of it, right? So the length of that line, of the gray line, divided by the red line, that will tell you the amount of liquid that's present. Now when we say amount, we're talking about the weight fraction of liquid because this is given in weight fraction. So what you do is you literally say, okay, our initial composition was at 40, so you do 40 minus about 20, let's say, or 21, divided by this line over here, which is maybe 61, divided by 21. So 40 minus 20 over 60 minus 20, essentially. And it's about half-half, right? That's going to be about 50%. That's 50 weight percent liquid, and it's the same amount of solid. Solid, you would do the green line, so you're going to start with 60 minus 40 divided by 60 minus 20, right? So this one, the way that I drew it, it comes out to be half and half. If we drew another one, and I'm not going to draw it on a figure because it doesn't seem to like that, but let's say you did this. Maybe this will work. What if I did this temperature, but at this point? Right? Maybe this is like 15. Maybe that intersects at 10, and this is at 70. What fraction would be liquid, and what fraction would be solid? The fact that your point is close to the liquidus line tells you it should be mostly liquid, but we can calculate it. We're going to do the lever rule. If this is in weight percent, then it's going to be the one away from liquid, right? Since liquid's on the left-hand side, we're going to take the right-hand section. It's going to be 70 minus 15. And we're going to divide that by 70 minus 10, the whole distance. Is everybody following, or is anybody lost? Yeah, Sam? Absolutely. That's a really important distinction. This tells you the amount of the phases. It doesn't tell you the composition. The composition we get by dropping tie lines down. So let's just do this real quick. 70 minus 15. Divide that by 70 minus 10. And that I get 91%, 92%. So that means that 92 by weight percent of the substance there, of the phases there, is liquid. And the liquid has a composition of 10 weight percent of whatever this is. Any questions? Everybody feel like they could do the lever rule to get weight fraction? If this was in atomic or mole fraction, then when you do the lever rule, you get a mole percent as opposed to a weight percent. Okay? If you get a mole percent and I ask in the end for how many grams of something it's produced, then you need to convert from mole percent to weight percent with the molecular weight. And you'll do that on the homework that's due on Wednesday. Okay? So let's do a quick example. So what is the weight fraction of alpha phase if our initial composition is 35%, it intersects the alpha line over here at 42, and it intersects the liquid at 31. Let me pull this up if I can. Okay. So go ahead and give your best shot at this. Give the answer as a percentage, but don't put the percent sign. So again, the key to this, the phase that you're interested in, since liquid is on the left, you want the tie line that's on the right. Since solid is on the right, you want the tie line that's on the left. Okay, that's the lever rule. So give this a shot. If you need help, raise your hand. What's up? So you're going to do, I'm asking for solid, so you want 35 minus 31. So the opposite. Oh, the opposite, yeah. So we're. So what is the weight fraction of alpha? That's the one on the right. So you take the tie line on the left.
Yeah, the tie line.
Yeah.
Okay. I think that might have confused me.
Okay. Percent, but don't put the percent sign. So if you think it's like 48%, just type in 48. And I always put a pretty generous range on it, so. What'd you come up with? What is the fraction of alpha? So it's closer to the liquid than it is alpha. So I think that there's a problem. So try that again. It should be 35 minus 31, right? That's your initial composition minus the left-hand side. 35 minus 31 divided by, what's that, 42 minus 31. What's that come out to? Oh yeah, so that's, give that a shot. I think you're off by just a little bit.
The alpha, you said that this value is the liquid amount, and this is the.
So this line, since it's on the left-hand side, corresponds to the right-hand side phase. And this line over here corresponds to the left-hand phase, which is liquid. So you want this thing, B minus 31 divided by 42 minus 31.
So what is that saying that the phase closest to the line is the phase that's opposite?
It's opposite because, you know, like if this point is really, really close to the liquid line, then you almost have 100% liquid. So it must be this other side divided by the total to get a high fraction. That's the only way that works. Yeah, what's up?
So this is so basically the big difference was the 42% minus 35% gave me 7%.
No, let's see. So you want this tie line, the short length there. That's going to be 35 minus 31 divided by the long length, which is going to be 42 minus 31. So 35 minus 41.
So you want the alpha. So that's,
We're looking for alpha, right?
okay, so it's liquid, then you do it the other way.
Then it's the other way. Yeah. But mathematically, it's the only way that works, right? The point that gets closer to that line, it should be pure that phase. And if it was the other way, it wouldn't work. Okay, get your answers in. We'll work this one out together. Okay, I'm going to close the poll. Okay. People think what? Okay, most of the answers are around 36. Okay, so how do you do this thing? Let's just work it again. Since we want alpha phase, that's the phase on the right, we're going to take the left-hand tie line, right? That our initial composition C naught is 35, so the left-hand side is going to be 35 minus 31. That's going to be divided by the total length, which is 42 minus 31, which comes out to I get a mistake. Sorry, let me fix that. Yeah, I get 36%. Okay? That equals 0.36. That's a fraction. So if you want to turn that into a percent, just multiply by 100 and you get 36.3. That's this is in weight percent nickel, so that's going to be weight percent alpha. Okay? Any questions, Ashton? Good question. If point B, let's say we were all the way over and it was completely in the alpha region, do we do the lever rule? Are there two phases there? It's just one phase. So that we can't do the lever rule except where there's multiple phases. So that doesn't work there. Okay, good question. Any questions about the lever rule? It's a handy tool. It allows us to sketch the structure quantitatively. We can say, you know, there's 30%, and by the time you finish it, there's 100%, but you can actually sketch all the stops in between. You can comment on what the composition is doing by following where it intersects these lines along the way. It's terrific. Super terrific. I might need to remake these notes. Okay? Now, what if you wanted to turn this into, we already talked about going from mole fraction to weight fraction and vice versa. How would you turn it into volume fraction, right? You've currently got a weight fraction. How would you get a volume fraction? In the way back? 36.4, and you got it wrong. Will you shoot me a text or an email, and I'll double check to see what's up. Maybe I programmed it wrong. I'll check that. It might have been that you just didn't give the exact answer, but you're in the acceptable range and you got value. Because I put generous ranges on these things usually, but shoot me an email and I'll make sure it's right. How would you convert from mass fraction to volume fraction? You just need density. Use density to go from mass to volume. Once you got the total volume, figure out your volume fraction, right? So you would need to know the density of these different phases at those specific compositions, which is not always the easiest thing to get, but you can do it. And there's some examples of that on YouTube, okay? We already talked about non-equilibrium cooling and coring. So a deep eutectic is like soldering iron. You have a question on this on your homework. If this is pure, let's see, this is pure gold and this is pure silicon. The reason that they do VLS growth with gold is because gold and silicon have this super deep eutectic that melts at a much lower temperature than either pure silicon or pure gold. So if you start out with a pure gold droplet on the surface and you add just a little bit of silicon, right? If you even go a little bit over, all of a sudden at 500 degrees you have a mixture of solid gold and liquid mixture of those two things. Or if you're on the other side, right? Let's say you add a lot of silicon, you're going to have a mixture that's somewhere along here, and you can control how much of each phase you have with the lever rule there. Okay? So deep eutectics are helpful. They do it for soldering, right? Solder. They pick things that have a deep eutectic so that they melt really easily. They design the solder to have, you know, right near the eutectic, so you don't have to take your iron up to crazy temperatures. It melts right here, right? In fact, eutectic means easily melted, right? That's what the Greek words for it mean. Okay? Now the lamellar structure forms. We talked about this last time. We were drawing this picture and we said it's kind of like this. It's these sort of like stripy bands. Why on earth do these bands form that we call the lamella or the lamellar structures? Well, think about it. If you were right above here, I'm not going to draw it because it'll probably disappear, right? But if you were just above 18.6 in the liquid phase, then that means that you have 18.6% of your atoms in that liquid phase are silicon. But as soon as you go below that point, it's going to phase separate into pure silicon and pure gold because there's no solid solubility in this binary eutectic. It's just like bringing the hits today. Okay? So what has to happen? You had a mixture that was some silicon and some gold. We're going to have to completely separate those two, and that means atoms have to diffuse. So if these students were, say, 50-50 even, right? If it was 50-50 of student A, it's 50-50 of student B, but as soon as we go below a certain temperature, I say you can no longer be with another student of the other type. You have to immediately segregate, and you only got 10 seconds to do it. Then the students are going to try as quickly as they can to clump together, students A, students B. We do like boys and girls, right? The girls would hurry and try and clump together, the boys would try and clump together. But if there's only 10 seconds for that to happen in, then they can't separate very far, right? They can only go a little distance. And so you get what are called lamella forming, right? If this is your mixture at first, you've got atoms A and you've got atoms B, and they're happily mixed together. But as it solidifies, there's no intermixing of these two things, then you're going to get regions, right? You're going to get the dark regions, and you're going to get the light regions, right? Where they phase separate. And the thickness of these lamella depends on how quickly atoms can diffuse, which is a function of the temperature and the type of atoms and all these things. Yeah, Julia?
Is that for solely solid and liquid composition, or is it for solid and solid?
Good question. No, it can happen for solids too. So steel does this, right? Steel, when they make different types of steel, which we're going to get to in a second, it starts out in a pure solid phase called gamma steel, which is a mixture of iron and carbon, right? It's two different atoms. But when you go below the eutectoid temperature, we'll show this in a minute, then you get bands forming. They call this pearlite, martensite, well, not martensite, pearlite, bainite. We're going to discuss these in a minute, okay? So that's why these lamella form. And so the book has lots of examples. As you cool these things down, the little islands form when you're in the, we call this region in the middle, above the eutectic. That's our pro-eutectic region, meaning we're above the eutectic temperature. But as soon as we go below that eutectic temperature, then you start to form the lamellar structure. Because all the liquid that was there, as soon as you cross that line, all of your liquid undergoes the eutectic reaction, which means it turns into two different solids, right? Alpha plus beta. And it happens very quickly, which doesn't allow them to phase separate as much as they might like to. Okay? Any questions on this? No? Mostly clicking? So a few more of the important types of reactions. We've talked about eutectic. We've talked about paratectic. There's something called a eutectoid. A eutectoid is shown right here. Let's see, is that right? No. This is what? This is two different solid phases. When you cool it down, it becomes a third solid phase. So that is a paratectoid. This is a paratectoid right there. We'll show you eutectoid in a moment. Okay? We've already talked about the fact that phase diagrams don't have to be between pure elements. They can be between compounds, like you've got over here KCl and MgCl2, and you can form a couple. These are intermediate compounds that are line compounds between them. Okay, something that's important to know we're going to come back to later when we get to kinetics is that these tell you what's supposed to be there from a thermodynamic standpoint. Thermodynamics assumes that we reach equilibrium. So if you took this, this mixture, if you took zirconia and you dope it with yttrium oxide, things you've never heard about and probably don't care about, you can actually make something that we all care about quite a bit, right? So if you heat it up, say, in this region, then you would expect T plus F. That's the two phases. Doesn't matter what those are for right now. There's just two phases, right? And what happens is that as you cool it down into this region, you would expect, since it's T and F here and it's M and F here, you would expect all of your T phase to transform to this M phase. That's what the diagram says, right? But look at the temperatures. This is at 500 Celsius. That's low in terms of ceramics, right? And so you're relying on them to transform, but you're not giving them a lot of thermal energy for it to happen. And so what can happen is that you quench in a high temperature phase, right? You make it metastable. So what happens is you cool it down here and all your tetragonal phase, that's the T phase, all that tetragonal, it stays put and it doesn't transform to the M monoclinic phase. And what that does is really important. This is how they make something called ceramic steel. Anybody own like a ceramic cutting knife at home? Surely somebody. A bunch of barbarians cutting your tomatoes with steel knives. Well, some of us appreciate a ceramic blade, and we cut our tomatoes with them. But a ceramic knife, if you were to drop that on your floor, it's going to shatter. Ceramic is incredibly brittle, but you can sharpen it like crazy. So ceramic, this phase diagram allows you to kind of get the best of both worlds. It's a ceramic, so you can sharpen it very, very sharp, but because you have this T phase down here where it wants to turn into M, when a crack does start, that provides a little bit of energy that it needs for T to turn into M, and when it does so, this is amazing, it's a little bit of a volume expansion, and it closes the crack. Can you believe that actually works? That sounds like something like my kid would come up with that solution, like maybe make the phase like expand and close the crack. Like, that works! It's incredible, right? So that, we're going to talk more about this later on. It's a metastable phase that kinetically is limited. It can't turn into the M phase until you give it a crack nearby. We'll talk about this more next time.